there. Okay, but we want to go to that bound again. Okay, and so we're going to take this finite rank subgroup. What was our procedure? We took this finite rank subgroup. We associated to it a monokernel. Okay, and then once we take this monokernel, okay, we had that this guy here, the Colchin closure is contained in the monokernel. So this is a differential algebraically closed set. It's contained inside here. Okay, and in particular, we have a map here, right, from the intersections in the jet spaces, right? So the points of these jet spaces, right, map to the points in here, and we know that this is finite. Okay, so so these are dominant, but it turns out also that there's this amazing theorem that says that when you go up enough, that these things are going to be isomorphisms, right? In particular, when you take this tower down, right, they're actually going to be closed immersions. So when you go all the way down, okay, and we can use this, right? We can use this because now we can try and compute like how many components this has, right? So we compute how many components, how many points are in this, because there's always going to be an irreducible component above every one of those points. Okay, so this is just algebraic geometry again, right? And there may be more components coming down, but if we bound the number of components here in some way, then we can bound this number, right? And okay, and this is what I wrote down here. Okay, and so I cheated a little bit. I mean, like I wrote something very ambiguous here. We need to take the Zariski closure of these things. So in order to get these bounds, you need to compactify in some way. Okay? And so this is what I meant by taking the Zariski closures of those things. And so we need to embed them in some ambient projective space and then take intersections and apply intersection theory. Okay? So, so here, Alex, so now what you do is you try and find some degree bound. So Alex, what he did is he uses this process called Sayre compactification, right? And then in this process, you have lots of divisors at infinity, and Alex, I'm pretty sure, did not care, and he's like, wanted this super tremendous bound that he loves, right?
Yeah.
Yeah. But it's funny because it's now been 20 years and nobody's done better, right? And he thought it was funny, I think, at the time, but yeah. So, I mean, there are some better things in other cases, but, and actually, I guess, due to Hershkovsky and Pillay, right, there's a thing that says if you have some intersection like this, then from just abstract considerations, the worst you're going to get is doubly exponential. So, okay, and all right, so there's this. Okay, so now I want to kind of show you how these degree computations work. Again, like I said, there's two things that I wanted to talk about, and now I wanted to talk about the torsion points. I hate the algebraic closures everywhere in the top. Okay, and I want to talk about this. Okay, so. It actually is going to turn out that there's two factors here that look similar, and those two factors, right, are actually going to be degrees of certain spaces. Okay, so so I wanted to talk briefly about the proof of finiteness for this in this case. So maybe I can go back to the board again. Mm-hmm. Okay, so yeah.
You can start it. Showing.
All right. Okay, so there's a really good paper by Bjorn Poonen. Oh, sorry. And it's called Computing Torsion Points. Sorry. On curves. And and he gives a really good four-step process to how Mann and Mumford's done, and he actually gives an algorithm for computing torsion points. And so there's four lemmas, right? So the first lemma, so 4 lemmas. Sorry. Okay, the first is due to Coleman, which is the hardest. And it says that, G of C is bigger than or equal to 2. Okay, and you take P bigger than or equal to 2G. Right, so I'm going to fix a curve over QP. Okay? Okay, so it could be defined over Q, and then you can view it over QP. Okay? So QP is the p-adic integers. Okay? And what it says is that C, let's take, we're using x's. Oh, sorry, you can do x. So I don't mess up the notes. Okay, so what you can do is you can do x intersect the torsion points. The torsion points are actually contained in, there's an unramified extension. Okay, and this will play a crucial role. So again, A is, so again, A, this is a curve. Okay, and then the Jacobian of the curve is A. Okay, and it's also defined over QP or Q. Okay, and so this is something that we'll need. Okay, why? So the unramified version is nice because this is actually equal to, and then maybe you recognize this from Alex. Right, so this is actually A ZP unramified since it's projective. Okay, so there's models, yeah. So I guess you have to say that there's a model of this situation. So by model I mean that you can define something over ZP and that this all makes sense. Okay. So I should also say that dang it, this is an X, and then I also need that reduction mod P makes sense. And that, yeah.
That A over the integers is not necessarily a Abelian scheme.
Where?
It's an extension.
No, these are Abelian. They're all Abelian schemes.
No, down below.
This one here.
Yeah, that A, you're putting it over the ring of integers.
Yeah.
And so it's not necessarily an Abelian scheme.
Yes.
It's an extension of a vector group by.
It's a neuron model. Yeah.
Yeah.
Oh.
Yeah. I think it's a neuron model. It's a model over Z. Right? Yeah. So you can start. So in particular, we should start with everything defined.
Extension.
No, it's not. No, it's not an extension yet. We're going to get there, but it's not quite. I mean, it depends on how.
It's the Jacobian of a curve that may have some by reduction.
So I'm at P it has good reduction. So I'm assuming that it has good reduction at P. So so let's actually, for simplicity, let's just take everything to be defined over ZP unramified completed to begin with. And then we don't have to worry about these things. Okay, so like you just suppose that it already.
No. If the curve has double points when you reduce it, I mean the curve has to be smooth over ZP in order for the A to be the Abelian scheme over the.
Okay, yeah. Let's take X to be smooth over or ZP. Let's take X to be smooth over ZP, and then take the Jacobian to also be defined over ZP.
Fine.
All right. Okay.
And you can do that by choosing a good enough P?
Yeah, that's my input.
Yes.
Yeah. Yeah. It's actually going to be the smallest prime of good reduction.
Okay.
For in the case that we're interested in. Okay. And so good reduction means that reducing modulo P makes sense, right? So, okay. So then there's a theorem of Katz. I mean, I don't know if this is really Katz, but this is a formal group thing, and it says that okay. So again, I'll do this again. ZP and ramified these torsion points here. There's a natural reduction mod P map. So the residue field of this is FP bar. And this map is injective.
That's not the reduction map. It's reduction map followed by an base field extension.
So all I'm doing is, this is a ZP.
I agree it's injective, but it's not just simply a reduction map.
So it's the specialization map. So
because the reduction map will go to FP,
This is FP.
No, you're
FP bar. So, okay, excuse me. So I'm just taking the points here, right? Yeah. So, I mean, the FP bar points are the same thing of ZP unramified completed, if it's over ZP unramified completed, is the same thing as the points in the special fiber, so you could reduce to. Yeah. So, okay, so the third, okay, so this is nice, okay? So there exists a psi such that A from ZP mod P squared to A of FP bar, okay? So this thing here, so this, the kernel contains, okay, so contains the torsion points. So by that I mean it contains the reduction mod P of the torsion points. So a reduction mod P squared of these torsion points. Okay? And then the fourth thing is that, so now I think I do need to use the jet spaces. So there's a surjective map from, so this is over, okay, so when I write subscript zeros, so in general, I'll make this convention. So this thing, and then I'm going to call this y0. Okay? Okay, so you have this thing. So this is the first modulo P. Okay? And so the number, okay. The last thing is that this number is bounded.
What's that? GA?
Yeah, GA, the additive.
Right.
What's
R. Let's see.
GA to the
G. GA to the G.
what's the 1? Is that a prime?
This is a 1 here, and this denotes the first order jet space. So this thing here, in the previous notation, was JP1 A over ZP unramified completed with respect to delta T or something like that. So this is the width vector thing, but I'm going to reduce it mod P now. Okay? So there's an important property here. Oh, so let me just write down the last part of this statement. Intersection, the kernel. Okay, so so this is finite, and then so from the four things, then you can deduce the conjecture, right? So or deduce minimum vert. Okay.
first p-jet space.
Yeah. So this is the first p-jet space. So let me.
Not the second.
The first. So A10 of FP bar will actually be, so this is going to be A of 1 of W, so W P1 of FP bar. Okay, so these are, and this thing here, it turns out that this is isomorphic to ZP ramified by P squared. Okay, so what happens is, okay, so maybe I can explain this now, okay? So this is like the tangent space dual numbers thing, okay, going on, okay? And so what you've done here is you've kind of traded off dimension for mod p-ness, okay? And so the idea here is that, so you have these z mod p squared, the ZP unramified by p squared points, and here, this thing's defined over fp, but now the dimension has gone up by a factor of 2. Okay, and so there's a trade-off between these things. So now you can view these points as a variety over fp. And sometimes this is called the Greenberg transform since I've taken the p-jet space and I've reduced it mod p. Okay, so this is kind of how these things work. So let me actually, let me show you actually like a simple version of like what this psi is. So psi, this is complicated. Okay, so
now what happens if you have supersingular reduction?
so if you have supersingular reduction, so then your EP is not what you, I mean, so the number of p torsion points is not what you expect it to be. So,
Right. So you have no p torsion points over fp bar.
Yeah. So
there's a extension of alpha p by alpha p in there.
I don't know. I'm assuming everything's smooth and good reduction. So let's see.
I mean, that's
Sorry,
where
is that
somehow
effective?
this should
I don't
this
know.
information should be trapped right there.
I mean, there is, okay, so there is,
That's why we do
yeah,
it
there
this
is
way.
relations between these things called the Serre-Tate parameters and these invariants associated with the jet spaces called, well, I've called them the lineal Z classes, and they're like arithmetic Kodaira-Spencer classes. Essentially, this thing here, it turns out to be a torsor under the Frobenius tangent space, and that class contains information about those about their Serre-Tate parameters, and there's a paper by Alex in Invenciones. It's called Differential Characters of Abelian Varieties Over P-adic Fields, and it gives cases. It talks about the sensitivity of, I guess, those classes that he constructs to supersingularity in phenomena like this.
It's neat.
So let me give you the silly proof. Let me give you the sillier proof. Okay. So so we have this first jet space. Okay. So A is an abelian variety. A is equal to the Jacobian of C. Okay, C is defined over ZP unramified, or let's say ZP. Okay, and so this is also defined over ZP. Okay, and one can construct the first P jet space modulo P. Okay, so this is the first P jet space. Okay, and then let's consider gamma a subgroup of this thing here, A1, 0, and so this thing here, again by adjunction, this is the same thing as A, and then of P squared. Okay, and so I'm going to actually just take so this thing here will be the prime to P torsion points. Okay, and okay, so since it's prime to P, what I'm going to do is I'm going to take the psi to be multiplication by P. So if it's prime to P, multiplication by P won't do anything. Okay, so what you can do is you can take A01 of FP, so I can take this, okay, and then I can multiply by P, 0, 1, okay, and so this is the multiplication by P map, and this thing doesn't hurt torsion, doesn't do anything to torsion. So the image contains the torsion points. Okay, so so thanks. Okay, so the first fact that I'm going to use is that there's this canonical map here. So from this guy, so there's a map. By canonical map, I mean it's just the structure map. So this is like from the tangent bundle to the original variety, and this is all done mod P. Okay, and the fact that's interesting is that the map here induced by natural projection is an isogeny. So it has finite kernel, right? And moreover, the degree of this map is less than or equal to p to the 2g. This is because multiplication by p factor. So this So this comes from multiplication by p. So that's the degree. The degree of multiplication by p on abelian varieties is this, and then. So I guess this is a piece of this. So this map factors, and one of those is those factors. But I don't see why that's true right now. But let's take this fact, okay? And let's take another fact.
Just look at the map from A0 to A0 multiplication by P. That factors, and the degree of the multiplication by P map is P to the 2G. Isn't that all there is?
So, but there's not a multiplication by P map on which variety are we considering
A0.
multiplication by P map?
A0.
A0. And then
In fact, you got P times A10, P times the arc space says that action will factor through, doesn't it?
Oh, I see what you're saying. You're saying this? Okay, and then so basically you take the image of this, and then I guess you'd have to show something like that. That has.
I was showing you. The usual argument with dual numbers is that you then have a diagonal map from the bottom left to the top right. If you have P A01 there.
Yeah. So bottom left to top right.
A0 to a P times A10.
Oh, you're saying, okay, so you take the image in here. That's true. This is there. Oh, but you're saying that you have, what, this?
Yeah.
You must. That's true.
Okay. Yeah.
And
Oh, so is this the dual isogeny for that thing?
yeah, I mean, you're just factoring multiplication by P through that, aren't you?
Yeah. So I guess this would, is this the dual, so like this, from here to here. So there's a map from, is this true that the image is in here? I don't know, we're gonna talk about this in a second. Okay, so let's get back to this thing. Okay, so the other fact that we need is that, so if C, the genus of C, did I call it X or C? X is bigger than or equal to 2, right? Okay, this implies that this JP1 of, we have X1, 0 is affine. Okay, so this is a cool theorem, okay? Okay, so now what do we have? Okay, so the torsion points, the idea now is that the torsion points, so here, so this is projective, isogynous to an abelian variety, and when I take this curve here, this is affine, and so if you have something, projective variety which is also affine, it must be a point, or it must be a unit of points. Okay, so this is finite. This is finite. So this is both projective and affine. Okay? And the fact that this is affine, so this comes from, so another presentation of this due to Martin Duchamp and as like a projective bundle. So this is, I can talk about this more if you guys want. I don't think we have much time, but.
Where's the other fact?
Okay. All right. So I was gonna. Hopefully, I'll type something up on this stuff. So since we
Yeah, I
took
was just
notes,
gonna
but
ask if you're gonna do that.
yeah. So I started typing it up, and yeah. So thanks for having me.
Can we post it?
Yeah, I'll post it when I have it. Yeah. Yeah.
Thank you.
Okay,
Well,
cool.
thank you.
Questions, comments? More questions?
What if you project from A02 down to A01? Is that,
So yeah, you also have. So yeah, you project from this thing.
is that a misogyny?
From P times this.
Yeah.
No, the dimension's too big, I think.
Oh, okay.
So I think, so this would be, so this is like Z mod, so P times A Z mod P cubed maps to, sorry, did you say A01?
Yes.
Oh, yeah, probably, sorry. Yeah, I probably, I don't know though, I don't know. I'm not sure, actually. Probably shouldn't say that. I don't know.
Can you go back to when, what was it, the Manning kernel gave you the
Yeah.
argument you wrote before the Manning
So,
kernel
yeah,
gave you
so-
a contradiction? or
Yeah. So the Manning kernel. So I can write that. I can write it down again. So. Yeah. So the idea is that so you had you had two things going on, right? So one is you had this psi map, which was Ueno's map, right? And you, after taking psi, you have this thing that doesn't descend to whose Albanese does not descend to the constants.
Yeah.
And so if you were dominated by a Manin kernel, if this guy was dominated by a Manin kernel, it would imply descent, right?
Mhm.
Which would contradict this Albanese does not descend, right? So in particular, you know that it's not dominant and it has to be in a proper subvariety.
But what was it? Was it connected to it being finite type, the Manning kernel?
Yeah, so like that part is used in, so that part's used in the dominance theorem, or whatever you call it, this trick, yeah. So, yeah, that thing's also used to compute the intersection numbers. So, like, when you want to compute the intersections, you need, well,
Yeah.
yeah, yes.
So, and this Manning kernel, it lives in what kind of jet space again?
So the Manin kernel lives in the 2G plus R jet space, where R is the rank of the subgroup that you're interested in.
2G.
Yeah, that's where it stabilizes, at least. It can stabilize before that.
yeah, I know, but I guess I mean, just in motivic integration, that stuff goes to zero when you evaluate it. I mean, it's like a measure zero set. So I'm just saying.
So I mean, you can take it all the way up though. So it's like you know how you take these limits in there. Yeah. So like if you take the limits in the motivic integration, I guess it's like you get something finite. So like
it would be the motivic volume would be zero on that. Well, I mean, if there is. I'm kind of confused what jet space we're looking at.
It's just like a finite. It would just act like a normal variety. Yeah.
Yeah.
So you don't need to like normalize. So like sometimes you do. I think in these you divide by like powers of L. I think in some of these computations where you take limits of R.
Yeah. Right.
Yeah. So.
Okay.
I think. Yeah. I'm learning that stuff too.
Oh, okay.
So, I'm not an expert
maybe you
in
can write. I'm just actually my question or my comment is maybe you can write it in terms of a motivic measure. This is like something.
So like yeah. So I was actually thinking that you could that's what I was thinking. So like if you can compute the Euler characteristic of a finite set, then so the Euler characteristic is just the dimension of H0 of that thing, and so you'd be able to just count the points. It'll give you the point count. So if there was some way so there's actually in the invariant way that motivic integration is set up, there are tricks that they use where they actually, so one of these bounds that Alex proves, he wants to get a bound that's only in terms of the genus and the rank, right? For Manin Mumford. And so what he does is he actually switches between a normalization and there's a trick where he considers two intersections, and there's two different jet spaces that you do, and one's like a resolution of the other. But it turns out that the preimage of the Manin kernel in this thing is not finite type anymore, right? But there's an exchange between these two like things, and there maybe is like an invariant. There might be an invariant way of formulating this in terms of motivic integration, but allow you to compute these intersection numbers better. Yeah, but I don't know. I mean, that's like speculation.
Well, when you write it up, I'll just be curious to look at that part. Yeah.
More questions? Well, thank you very much.
Thanks for being patient.
Yeah. Because I don't work with because I work with linear groups. I'm U.S. general, sorts of things. Like, what about the J and variant? That's another.